In 1905, Albert Einstein resolved the long-standing contradictions between mechanics and electrodynamics, but the special theory of relativity contained a hidden constraint that would occupy him for the next decade. This formula represents the Minkowski spacetime interval. It calculates the distance between 2 points on a rigid Cartesian grid, where every line is straight and every unit of measure is uniform. This math relies on a Galilean domain, a reference frame that is perfectly rigid and non-accelerating. It assumes that observers can use standard rulers and clocks to define position with absolute geometric clarity. However, the laws of classical mechanics are restricted to these specific uniform systems. If a reference frame is accelerated, or if gravitational forces act upon it, the symmetry of this rigid mathematical framework is broken. To incorporate gravity, the Cartesian grid must warp into an irregular structure. The flat Minkowski equation morphs into the generalized metric tensor, where the distance between points depends on a set of variable coefficients. We are going to trace Einstein's logical path from a simple thought experiment to the non-Euclidean Gaussian coordinates, where the geometry of space itself is the gravitational field. Einstein quickly realized that building a complete theory of gravitation required the total destruction of rigid Euclidean space. Einstein began with a thought experiment involving an observer inside a large chest, located in a region of space so remote that it is far from any stars or planets. A rope attaches to the lid, and an external force pulls it, causing the entire container to accelerate upward at a constant, uniform rate. This diagram compares two scenarios. On the left, the chest accelerates through a vacuum. On the right, an identical chest remains stationary on Earth, subjected to a uniform gravitational field. The observer inside the accelerated chest releases two distinct objects, a piece of lead and a piece of wood. In both chests, they fall at the exact same rate. Because the floor accelerates upward to meet them, they strike the surface simultaneously. This occurs because of the law of the equality of inertial and gravitational mass. An object's resistance to acceleration is exactly proportional to its weight in a gravitational field. Consequently, there is no internal experiment the observer can perform to determine if they are accelerating through a void or resting on a massive planet. An accelerated reference frame is physically equivalent to a localized gravitational field. To see how this affects geometry, Einstein looked at a continuously accelerating system, for instance, a rapidly spinning disk. Because the disk is rotating, its outer edge undergoes constant centripetal acceleration, simulating a gravitational field relative to the center. This diagram shows a spinning disk, labeled K', placed over a stationary, non-rotating reference grid labeled K. An observer measures the radius of the disk, the distance from the center to the edge, using a small measuring rod. Because the rod is perpendicular to the direction of motion, its length is unaffected. The measurement matches what a stationary observer would record. Next, the observer uses the same rod to measure the circumference of the spinning disk. Here, the rod aligns with the direction of rotational velocity. According to relativity, it undergoes Lorentz contraction, physically shrinking relative to the stationary grid. Because each rod is shorter, the observer must use numerically more of them to complete the circle than if the disk were at rest. Dividing this expanded circumference by the unchanged diameter yields a value larger than pi. In the presence of a gravitational field, standard Euclidean geometry is invalidated. Rigid rulers and straight Cartesian axes lose their physical meaning. If the rotating disk proves that rigid rulers produce contradictory results, we need a way to describe space that doesn't rely on Euclidean geometry. To solve this, Einstein adopted Gaussian coordinates. He replaced the rigid grid with a fluid, four-dimensional system, a mollusk, where the coordinate lines are arbitrary and non-parallel. In this system, the coordinates, labeled x1 through x4, have zero direct physical significance. They serve only as sequential labels to number events in space and time. But we still need to calculate the actual physical distance, or ds, between two adjacent events. This leads to the mathematical engine of the theory, the space-time interval equation. The dx variables represent the arbitrary mathematical differences between our coordinate labels. The g coefficients are the vital link. Their numerical values fluctuate depending on the position in the continuum, adapting to the local geometry. By multiplying the arbitrary labels by these variable coefficients, we derive true physical distance and time, accounting for the distortions seen in the rotating disk. These fluctuating coefficients define the curvature of space, making the metric tensor the mathematical representation of the gravitational field. This shift from mechanical forces to geometry allowed for a new kind of astronomical prediction. A massive body like the Sun alters the specific values of the g coefficients in the surrounding Gaussian domain. This altered geometry forces light to travel along curved paths, known as geodesics. Because space itself is curved, the straightest possible path for a star's light is a bent one. Einstein predicted that starlight grazing the edge of the Sun would be deflected by 1.7 arcseconds relative to an observer on Earth. This radical claim was put to the test during the total solar eclipse of May 29, 1919. The star positions captured by the expedition shifted by the exact margin predicted by the coefficients of Einstein's field equations. The results vindicated the theory, confirming that space and time are not a static background for physics. Einstein proved that the rigid universe is a mathematical illusion, replaced by the localized geometry of the metric field.